Okay, we're going to continue on, and we pretty much finished chapter 12, but we have just a couple of things to talk about, and then we'll roll into chapter 13 here. So last time in chapter 12, we talked about kinetics, obviously still. We talked about really the relationship between temperature and the rate constant. That's the Arrhenius equation. We saw something like RKT equals our E of A over R. 1 over T1 minus 1 over T2. Again, this is sort of that 2-point version of the graphing equation that we saw, where we can make a graph of the natural log of K, 1 over the temperature in Kelvin. And again, that will yield you a straight line where we can use the slope of that, which is minus E of A over R. Remember that the R here again is the gas constant that has the energy value in it. And again, not the one that we use for the ideal gas law or anything like that. Also, as we talked about, that also creates for people sometimes unit issues here, as activation energy is oftentimes given in kilojoules, and our R obviously is in joules. So again, you just want to make sure you watch the units when you're using that equation as well. We could also use the y-intercept here, and the y-intercept, which would be B, is equal to the natural log of A. A is that frequency factor when we're doing a graphing sort of version of it. And we can figure out really the proportion of molecules, thank you, that have enough energy to get up and over that hill. All right, so let's just finish out the last little part here about catalyst, which we sort of touched upon as we were going through the chapter, but a reminder that a catalyst is used oftentimes to speed up a chemical reaction. Again, it's not a product and it's not a reactant. And once again, it really does not get used up during the course of the chemical reaction. It is there in most cases to facilitate the reaction occurring sort of more efficiently and faster. And the way it's able to do that is, as I mentioned, it's able to find, maybe a better pathway or a more efficient pathway for that reaction to take place, which means ultimately what you're going to get is a greater number of molecules that have enough energy to kind of get up and over to the other side. And the result of that is because in the uncatalyzed reaction here, this is our activation energy, this big hill. By finding that sort of better pathway for the reaction to take place, we've dramatically lowered this energy barrier to get to the other side. And again, what that means is you're going to have more molecules that can get to the other side, and that usually will result in a faster sort of reaction occurring because we lower the activation energy. So ultimately, that's what a catalyst will do sort of energy-wise, is lower that hill or the activation energy, and thus will allow the reaction to take place a lot faster. So as the activation energy goes down, we will see an increase in the rate constant or the rate. And usually, again, everybody would want to walk this hill versus going up this hill, I imagine. So a lot longer to get up and over to the other side. Now, there are different types of catalysts. There are homogeneous catalysts and heterogeneous catalysts. And much like mixtures, a heterogeneous catalyst is a catalyst that's not in the same phase as what it's reacting. So maybe what's reacting are gases and the catalyst is a metal or a solid. So they're in different phases. The Haber process of ammonia is an example of that. Ammonia is a spontaneous reaction that takes all day unless you do it in the presence of a catalyst. So it does take a while. The production of nitric acid in our cars, or cars that have catalytic converters, there's solid metals in there, which is why people steal them, right? There's precious metals actually in the catalytic converter, and it helps sort of the process of reducing down hydrocarbons and stuff like that as it goes through your car in a combustion engine. A homogeneous catalyst is a catalyst that's in the same phase. So, for example, an acid catalyst, like adding HCl to your reaction, is in the same phase as all the other reactants and stuff that we did. Base catalyst. So a lot of times for those guys, you'll see, and this is typically where we see catalyst written on top of the arrow. So a lot of times we see like an H plus written on top of the arrow. That indicates that an acid is being used as a catalyst in this particular reaction. Here is sort of that Haber process of ammonia. And again, we have some solid catalysts being used. And as I mentioned before, without the catalyst, these guys got to kind of fly around and find each other. But one of the ways it sort of works is these guys are sort of attracted to this metal surface. And what that does is it allows all these guys to be in much closer contact with each other a lot more efficiently and a lot quicker. And it also helps a little bit with the breaking down process of each of those guys as well. And they can reassemble into ammonia on the back end here. So without sort of this platform, again, they would be sort of flying around trying to find each other and trying to start this reaction. Again, it just allows everybody more efficiently to sort of come together for the reaction to take place. This is the process of making nitric acid, a little ammonia, and a platinum catalyst. And we actually make a little NO2 in the process, and that NO2 will make some nitrous acid and nitric acid. And this is an interesting one because some of the products that we make actually go back and break down again and continue this sort of process to make more nitric acid as we go through here. But again, you can see the hot platinum wire sort of acting as a catalyst in this case. And there's our car and our catalytic converters. Again, there's precious metals in there. So as the combustion reaction, right, gives off the products that goes through here, and hopefully some not so bad things coming out of your tailpipe if you have it there. And again, this is what happens, right? They go under your car and they cut it off and they take it with them. So they sent out an email here years ago, like, if you see somebody walking with a saw in the parking lot, you might want to report it to somebody. And a lot of people coming through and taking people's catalytic converters as they're parked out there. All right, so again, the catalytic converter has a lot of those precious metals, which allow us to sort of break down some hydrocarbons and byproducts of our combustion reaction. Any questions on that there? All right, so that does officially wrap up chapter 12. So we're going to go off to 13 next. Seems like a good chapter. Let's go there. Only on chapter 12. And we're doing that on Tuesday, I think I said, right? I'll try to remember to write that quiz. So hopefully that's all right. So chapter 13 is chemical equilibrium. This is the big chapter. This is the topic of the season right there, which is pretty much every equilibrium that you probably did not want to know about. We're going to talk about it throughout the semester here. So let's just start with the basics here. So when we talk about equilibrium, it's really important to think about the type of reaction that we deal with chemical equilibrium. And it is a certain type of reaction. It is a reversible reaction that basically takes place. And again, a reversible reaction has these arrows that head in both directions. So it does have a forward direction, which goes obviously from reactants to products. And in these reversible reactions, what happens is at some point you will build up enough products that the products themselves will actually start reacting and kind of heading back in the other direction. So at some point you'll build up enough products, they'll go, let's just react with each other and go back basically in the other direction. And that is what is sometimes referred to as the reverse direction, heading in the opposite direction. And that is when we're going from our products to our reactants in this case. At some point, it will reach what is referred to as chemical equilibrium. And people have a very wrong understanding sometimes when they see the word equilibrium, and it's probably because the word says equal in it. People think that when it reaches equilibrium, that you end up with the same amount of everybody on both sides. And that's not what equilibrium means. What equilibrium really means is it actually deals with the rate, like we talked about in the previous chapter. When something reaches equilibrium, what that means is the rate of the forward direction. So as quick as those reactants go to products will then equal the rate of the reverse direction as fast as those products go back to reactants. So that is what it means when we reach chemical equilibrium. We're actually talking about the rate of those reactions, the forward direction and the reverse direction, basically being equal to each other. So what that really means is when it reaches chemical equilibrium, nobody changes in terms of their concentrations. So whatever concentrations they may be at that point, whatever pressures they may be at that point, they will be able to maintain those concentrations or pressures because they're at equilibrium, unless you do something to screw it up, which we'll talk about later on in the chapter. But if you don't do anything to it, they'll be able to maintain that. So, if we have this reaction, and initially we had 4 of this guy and 3 of this guy and none of these guys, and this thing goes through equilibrium and it reaches equilibrium, maybe we end up with 2, 1, 2, and 3 molar of these guys. What that means is once it reaches equilibrium, everybody will be able to maintain their concentrations. And again, nothing's going to change because just as quick as you drop some to the product side, it comes back the other way. So it's like balances itself out pretty equally. But again, it does not mean that we have equal amounts of everybody on each side of the arrow. It just means pretty much wherever they are at that point when it reaches equilibrium, that's where they stay, basically, until you do something to mess it up. Any questions on that there? So when we see a reaction that is at equilibrium, sometimes it appears to us sort of on the big scale. For example, if you did a reaction and it went to equilibrium in your test tube, your beaker, you may look at it and go, oh, it's over. It turned pink, or it's pink. It's just staying kind of that pink color. And you may think there's nothing going on, but there is actually a lot going on in that beaker or that test tube to maintain that pink color, for example, that you see. So although, we may look at a test tube and it just may look like it's done, if you were able to like super zoom in there, you would see a lot of reactants going to products. You see products going back to reactants again at the same rate. There's a lot of activity happening, even though on sort of the big scale, it just looks like, man, there's not much going on. It's over this reaction. And that's different than sort of a one-way street reaction, where it's not a reversible reaction. When we do like a one-way street with a one-way arrow, everybody dumps out to the product side and it's pretty much done at that point. But here with a reversible reaction, when it reaches chemical equilibrium, there's a lot of activity that's continuing to go on. And that's why it says on the molecular level, it's very frantic. There's a lot of stuff happening. And it's not static, even though it may appear to us in the big picture that is static, nothing's going on, but definitely in the sort of super zoom level, the microscopic level, there's a lot of activity to maintain that equilibrium. So here's like a reaction of a little N2 plus some H2, a little ammonia making. Like a good chemistry person, I'll balance the equation. I know. All right, there we go. So here at the very beginning of this reaction, we pretty much have only our reactants present. We have basically none of our products. Now, obviously, at the very beginning of this reaction, the only place for this to go is in the forward direction, right? Because all we have are reactants available to us. So as our reactants start to react, we will start to see a decrease, right, in the amount of our reactants. And we should, at the same point, start to see some products being formed, which means we should start to see, as we see here, some products being formed in this particular graph. At some point, it will reach chemical equilibrium. And as I mentioned before, chemical equilibrium means pretty much everybody's going to lock themselves into place. I'm going to keep pointing at you. I'm just going to keep doing this through the window. I'm just going to keep making hand signals to you through the window. I'm assuming you want to come and talk. I don't mind. I'm going to take a seat. Go. Okay. So we are now talking about something here. So once again, we're talking about equilibrium. And as this reaction starts, as I mentioned, pretty much because of the availability of really only our reactants, as I mentioned, pretty much that forward reaction is going to dominate at this point because, again, we have really no products to go the other way. But as we start to build up some products, what we start to see is a kind of decrease in the dropping of our reactants, right? It's not kind of dropping as much. And that's because at that point, we're going to get started of our reverse reaction starting to occur. So we're going to build up enough products on this side that they will start to react and start heading the other way. That's why at the beginning here, we have much a more steep decline in our reactants, and it's sort of leveling out. At some point, what will happen is we will have both reactions happening, the forward and the reverse reaction, and we will hit this point right about here. And that is the point where if we look at the concentrations of everybody, they have all plateaued out. Yeah. And when we look at a graph and we have a line that just goes straight, is the concentration changing at that point? It's not. It's pretty much staying the same, right? So that's what it means when it plateaus out. Pretty much they've all are keeping their concentrations. And that's where a chemical equilibrium has been reached. At this point, right here, that rate of the forward direction will equal the rate of the reverse direction. And again, what that's going to do, as I talked about earlier, is essentially lock everybody into place in terms of their concentrations. Once again, it doesn't mean they're equal. As you can see in this graph, none of them are equal concentrations. But what they're able to do is maintain their concentrations as long as you don't screw up the equilibrium. And they'll continue to maintain that all the way through. Any questions on that there? So here, as we look at this here with from water and CO, as I mentioned before, initially we have no products a lot of times. So just the availability, right, of these guys to start reacting is going to kick off the forward direction in this reaction. At some point, again, we will continue to build up some more of these guys. They're going to start to increase. These guys are going to start to go down. And that's going to be enough increasing on the product side that we will eventually sort of get that reverse reaction to occur. And again, it will continue at this process until the rates equal each other. And then we know that we basically have reached chemical equilibrium. And that's graphically, as you can see, pretty much when you look at the graph and your patient dies, pretty much you got a flat line where everybody's concentration stays the same. That's basically where everybody has reached chemical equilibrium. So let's take a look at this guy here a little bit more, this reaction. So if we did have this reaction, a little H2 plus some CO goes to H2O. I'm sorry, H2O good plus CO goes to H2 plus CO2. What would happen to everybody's concentration if we had this guy that was at equilibrium and we decided to add more water to it? So take a moment and think about it. How would the concentrations of everybody change if we had this system at equilibrium and we added some water to it? All right, so let's think about it here. So if I add more water to this, would the concentration of H2, for example, will it go up? Will it go down? Will it stay the same? It should go down or up. That is maybe both answers. That's in this case, let's think about what we're doing. We're adding water, right? Water's where in the equation? Water's right here. It's a reactant, yes? So what we just did by adding water is we just made a lot more reactants available, right? Which means would the forward reaction or reverse reaction probably kick off? The forward direction, right? So the availability of everybody there to start reacting, right, is going to cause, in this case, the forward direction to basically kick off because there's just a lot more reactants, right? They're going to be easier to find each other and start reacting. The result of that is when we get to H2, which is a product, should I have less or more of it being made? Yeah, we should start to see an increase, right, in our product of H2. And CO2, we should also see an increase as well, because again, the forward reaction is taking place. How about our CO? What should happen to that? It should go less because the only way to make the products and have the forward reaction, right, is for these two guys to start reacting with each other, right? So we would see a decrease in the amount of CO. How about water? What would we see happen with that? Yeah, so water's kind of an interesting one. It will overall go down, right? But it's going to first go up because you added it, right? So it's artificially going to go up. But once the forward reaction starts, it should then start to come back down. And it may actually end up higher than it started with just because you artificially added it, but it should kind of peak because you added it. But then once that forward reaction starts, it should start coming down with the other reactant, and it should overall sort of decreasing in that sense. Any questions on that there? Yeah. What's that? It will after it resets itself. So these reactions pretty much always wants to be at equilibrium. So even if you do something to it, which is what we just did here, we did something to this reaction that was at equilibrium. We kind of screwed up the equilibrium by adding some more water. But what it will want to do is sort of reset itself to get back to that point where the rate of the forward and reverse reaction will be the same. So it will eventually reach to equilibrium again. Yeah. Other questions? Okay. So we'll take it out the same one. What happens in this case if I add H2 to this reaction? What will happen to my H2O concentration? Will it go up? Will it go down? Will it stay the same? So when I add H2 in this case, H2 is a reactant or product. It is a product, which is over here. Does that mean what will happen will be the forward reaction or the reverse reaction in this case? Yeah, it's going to be the reverse reaction because now we have a lot more products available, right, to start reacting. So what that's going to do really is kick off the reverse reaction, right, from starting to happen. The result of that is actually in this case, we will start making more water, right? And we also should see an increase in the CO as we were making it. The CO2, we should see a decrease, right? Because again, in order for that reverse reaction to take place, we need both products reacting. And for our H2 in this case, it will be similar to what we talked about there with the first example. It artificially will go up because we added it, but once that reverse reaction starts, it will start to come back down in the same direction as the CO2. Any questions on any of that there? So what we're looking at right now is was really what's known as Le Chatelier's principle, which we'll talk about at the very end of this chapter. It's basically when you have a system at equilibrium and you do something to screw it up, and you can. So you could have a system, as we talked about, will stay at equilibrium the whole time, but you can do things to that reaction that will kind of mess up the equilibrium. The nice thing about an equilibrium reaction is it always wants to get back to that state. So even if you screw with it or screw it up, it's going to try to get itself back to an equilibrium condition. So it will self-adjust itself in a way that gets it back to that equilibrium condition. Yeah. Yeah, we'll talk about that at the end. And those are other things that you could do to a reaction, change the energy, heat, temperature, pressure, volume. So there's a lot of things that you could do to systems that are at equilibrium that will frankly mess them up. And depending on what you do to it, the system will sort of react differently depending on what you do. But the ultimate goal of the system is to get itself back to that equilibrium state. Other questions? All right. So there's the fold out slide there. So let's talk about the equilibrium constant, shall we? The equilibrium constant is capital K. And I write that because we just finished talking about lowercase k, which is that's the rate constant, right? So capital K here is the equilibrium constant. It is the letter that brings you this class. Chem 51 is brought to you by the letter K. We're going to talk about every single K, again, that you might not want to know about. So we'll talk about KC, KP, KA, KW, KB, KSP. I know I could keep going, KF, all these Ks. So this class is really brought to you by that letter. But again, important since we do talk about kinetics in here, little k rate constant, big K equilibrium constant. So when we look at this reaction such as this, there is a relationship that gives you a constant value, and that is the equilibrium constant. So here we could calculate basically or write the equilibrium expression by basically taking the concentration of our products divided by the concentration of our reactants. And a reminder that if you have this little bracket, that means concentration. And usually that is our friend molarity, moles per liter. So in this case, we would take the concentration of our products. We also, in the case of writing the equilibrium expression, take the coefficient as the exponent. So here, when we write the equilibrium concentration, our expression, the coefficients in the balance equation become the exponents. This is obviously 1. So much like in chemistry, we really don't write 1, but that's obviously 1 there in this case. So the concentration of NO2 squared divided by the concentration of N2O4 equals 4.63 times 10 to the minus 3. The number's not that important right now in terms of this particular number. In general, the way that you write your equilibrium expression is you take your products over your reactants, you take the coefficients as those exponents. And one of the nice things about K is, after being beat into your head for years that you should always have units, K is just a number, no units. So K is just a number. Don't have to worry about the units or anything like that. So it is just a number. Typically, no units. So what does this number mean, or what does this number tell us? Well, let me ask you, if I have a large value of K, what would that mean? When I reach equilibrium, would I mainly have reactants or products? I would have products, right? Just mathematically speaking about it, you got a large number divided by a small number gives you a large number, right? So when it would reach equilibrium, you would mainly have products. And if I have a small value of K, that would mean obviously the opposite here. You would mainly have reactants, right? And again, to get a small value of K, you would need a larger number on the bottom and a smaller number up on top, which means you would have more reactants than products. So K does tell us, for example, what we would expect to be there when we reach equilibrium. Would mainly be reactants, will mainly be products. So what is a large value? What is a small value? Well, a large value is that big number of, frankly, 1. Yeah. So anything above 1 is considered a large value of K. Anything less than 1 is considered a small value of K. So this number that we have up here would be considered a small value of K, which means when we reach equilibrium, would we mainly expect reactants or products? We mainly expect reactants in this case because of the small value of K. Now, there is definitely degrees of large and small. For example, you could have a K value that's like times 10 to the 54, which is super large, yes. And that's pretty much almost like a one-way street. But even at a large value of K like that, there's still going to be a little bit of it coming back the other way. So it is still an equilibrium reaction. Even if you have a super large value of K, you will still have it going in both directions, but it's mainly going to hang out on one side versus the other. And just like large value, we'd have a really small value, like as we will see when we get into like KSP, like to the minus 34 times 10 to the minus 34, which is a really, really small number, which means it's pretty much not going anywhere. It's going to hang out there on the reactant side. But again, even things with that really small, if it's in equilibrium, we'll still have everybody going in both directions. When we see an equilibrium constant, there's really only one thing that will affect the value of the equilibrium constant, and that is temperature. So temperature is the only thing that will affect the value of the equilibrium constant. Now, what I mean by that is if we are at, say, 25 degrees Celsius, and I do a bunch of experiments at 25 degrees Celsius for this particular reaction we're looking at, and I figure out the K value at 25 degrees Celsius. For all 3 of those experiments, should the K value be the same or different? Should be the same, right? Because the temperature stays the same through all 3 of those experiments, right? If I do the same experiment, the same reaction at 40 degrees Celsius, and I do it 3 times as well, the K value at 40 degrees, should they all be the same or different? They will all be the same at 40 degrees because the temperature hasn't changed, right? When I compare the K value at 25 degrees to 40 degrees, will they be the same or different? They will be different. So that's what we're talking about. So when we're talking about temperature affecting the value of the equilibrium constant, as long as you keep the temperature the same, you can do as many experiments as you want. You can use some reactants in one experiment, you can use some products in the other experiment. You can use a combination of reactants and products. It will always come to rest at equilibrium at the same ratio of products to reactants. So that is an important thing. And that is something that people have a hard time sort of understanding. For example, if I did experiment 1, let's just say we had A and B here, for example, goes to C plus D. Let's say in experiment 1, I used 2 of this guy, 2 of this guy, and none of these guys. And then I did experiment 2, where I used like 1 of this guy, 1 of this guy, maybe 2 and 4 of this guy. And then maybe experiment 3, I did none of the reactants, but maybe I did 2 and 2 of our products. All of those guys, when they come to equilibrium, as long as my temperature stays, say, 25 degrees for all of them, they will all come to the same equilibrium constant. And sometimes people go, well, I use different amounts, so how can I get the same number, right? And you can get the same number by just thinking it's a ratio. The ratio of products to reactants will always be the same no matter what you start with, as long as you don't change temperature. So I always think about it like this. A very simple example maybe to illustrate that is, I'm going to go with the number 2 here, yes? And I want my equilibrium constant to be 2. If I take 4 divided by 2, I get what number? 2. I take 8 divided by 4, I get. Take 2 divided by 1, I get. These are all different amounts, right? Different numbers. These all are made by different things, but the ratio of each of those things are the same. And that's what happens with an equilibrium reaction. Regardless of what you start with, it will always come to rest at the same ratio of products to reactants, and will give you that same equilibrium constant as long as you are not changing the temperature every time you do the experiment. Any questions on that? All right. All right, so if we look at this reaction here, we got Mickey at the start of the day, reacts with this guy here, and at the end of the day, Mickey's upside down. We end up with a equilibrium constant here of 25. When we reach equilibrium, should I mainly have reactants or products in this case? Yeah, I should mainly have products. 25 is considered a large value of K, which means I should have more products than reactants in this case. All right, so let's talk a little bit about homogeneous equilibrium. And homogeneous equilibrium is much like homogeneous mixture. It means that everybody's in the same phase. And we could write our equilibrium expression for this reaction here, which again is our products over our reactants. So here again, we would take our NO2, we would square it because of the coefficient. We would divide it by N2O4. And at this point, this is what is referred to sometimes as Kc, our first of many Ks. I'm going to go with C for concentration because it just seems like that might be what it means. And that is when we are writing an equilibrium expression using concentrations here. Now, since these are all gases, another very common property that we deal with, right, with gases is pressure rather than, say, concentration. And we could write a K expression for this that deals with partial pressures. And that would be the partial pressure squared of NO2. Once again, we still use the coefficient as the exponent, divided by the partial pressure of N2O4. And this is what is known as the Kp value, P meaning pressure. So clearly, in order to write a Kp, you need gas involved, right? You need at least some gas to cause pressure. So the Kc and the Kp value, typically speaking, do not usually end up the same numerical value. It is possible they could end up the same value, but in most cases, they're not going to give you the exact same number. But they will tell you the same thing. So if you have a large Kc value or a large Kp value, it means that you will have basically products at equilibrium when you get there. If you have a small Kc value and a small Kp value, you will also mean that you have reactants when you reach equilibrium. So there is a way to go between the two, and in certain cases, maybe you're given concentrations and you really want like the Kp value. So you could calculate the Kc and then convert it to Kp or vice versa. The Kp value is equal to the Kc value times RT. This R is our gas constant R, 0.08206. So that is the gas constant one, not the energy one that we used in the previous chapter. T is our temperature in Kelvin. And delta N is the change in the number of moles of gas that is present. So this is a way that you could go from the Kp to the Kc and vice versa by calculating them. The delta N should be our products minus our reactants in terms of the gas molecules. And that's important. So for example here, if I had 3A goes to 2B, and these are both gases here, delta N would equal -1 because it is products. So that's 2 minus 3, just the coefficients, -1. It's important the negative there, right? Because if I do 1 and -1, do I get a different number when I go into this equation? I do, right? Because -1 means you take 1 over it, right? And 1 means you don't do much to it at that point. So sometimes people make a very common mistake of they just take the difference and not worry about the negative or positive. You definitely should always do products minus reactants. And if you have a negative, it's going to give you obviously a different math answer there when you punch it into that equation. So you want to make sure that you do that. You're just going to go through and count up anybody with a G, and the coefficient, right, is how you could figure out basically how many gas molecules or moles that there are. Yeah.
Can you switch the order, switch the products and reactants?
Can you switch the products and reactants on?
There's why N2 over.
Are you asking why this is the reactant?
It's just because you started with that one.
Yeah. You cannot, and I think we're going to answer your question in a few slides when we get there. But to sort of answer your question right now, when you do see a K value sort of given to you, it is specifically based on how the equation is written. So it's specifically tied to what's the reactant and what's the product of how it's written, and is tied to the temperature as well. So if you were to sort of swap it out, which it is a reversible reaction, where the 2NO2 is like your reactants and the other guys your products, you would have to adjust the K value that was given to you. And we're going to talk about how to adjust that. So there's some adjustments that you have to do to it. Yeah. So that's why when you do see a K value, it is specific for exactly how it's written and at those sort of conditions and stuff like that. Other questions? All right. So let's take a look here. Now, when we have a homogeneous equilibrium, if we were to write the equilibrium expression for this guy, which is basically acetic acid breaking apart, going for a swim, we would do our products over our reactants here. Now, there are a couple of things when we write equilibrium expressions that we frankly leave out of the equilibrium expression because either they do not affect the equilibrium or their concentration pretty much remains constant throughout the sort of reaction. And one of those things is actually our friend water here that's in the liquid state. So water in the liquid state does remain relatively constant, which means if you were to write the equilibrium expression for this reaction here, you would actually leave it out. And this would be the proper equilibrium expression for this guy, where we leave out liquid water. Water in the gas state, okay, because it's flying around doing things. In the liquid state here, it is not going to change its concentration all that much. So in general, when you write equilibrium expressions, there are really two things that you do not include, and we'll kind of jump a slide or two here. We do not include, as we see here, anything that's a pure liquid, because typically its concentration will remain constant throughout the experiment. And the other thing that we do not include is anything that's a solid. And that's because, frankly, a solid is like a rock. It's just going to sit there and not do much, right? So it's not going to have too much of an effect on the equilibrium. So those are two things that we do not include. which pretty much leaves us two things to include. So we do include in the equilibrium expression anything that is aqueous, because it's moving around, is participating, and anything that is in the gas state. So those are basically the two things that you definitely include in the equilibrium expression. Any questions on that there? And as I mentioned earlier, again, it's just going to be a number that you're going to get, no units, because really the units don't always cancel out nicely. So we usually just leave the units off of the equilibrium constant. All right, so basically aqueous gas things go in, anything liquid or solid goes out and stays out. So why don't you take a moment here, write the Kc and Kp expressions for each of these if possible. Okay, so let's take a look. So for the first one here, we're going to write our Kc. Again, it's going to be the concentration of our product, so that would be our NO2. Once again, we do need to take the coefficient here, so that's going to be to the fourth, times the concentration of our O2. Again, the coefficient here is 1, so we don't have to worry about putting the 1 there. We're going to divide that by our reactants, which is N2O5. And again, we're going to take the coefficient there and do a square. These are all gases here. So we can write a Kp. So our Kp will basically be the same, except again, we're dealing with partial pressures. So it'll be the partial pressure of NO2. Once again, we do need to take it to the fourth times the partial pressure of O2 divided by the partial pressure of N2O5. And once again, we do need to square it in that case. Any questions on that one there? Coming to our bottom one, we're going to do a Kc, which will be our products, which would be H3O plus times our F minus divided by our reactants, which is HF. Am I including the water here? I am not. Again, it's a pure liquid, so we're not going to include it. Can I do a Kp for this guy? I cannot, because there's no gases. So you need some gas in there to write a Kp. I would say either you'll have all gases, or you could have some solid and gas sort of combination to write a Kp, but you definitely would need obviously gas molecules still present. Any question on any of those? Now we'll talk a little bit about it later on in this chapter, but speaking of Kp, when we start to do calculations, or typically speaking, when we do calculations involving equilibrium and it involves pressure, the unit of pressure that we should always use is atmosphere. So a reminder that 1 atmosphere, right, is how many torr? 760, and 760 millimeters of mercury, right? So later on, probably a little bit more so than up front here in the chapter, if you may have some problems where you're doing some calculations with pressures, and they may even give you the pressures in, say, torr or something like that, and they may even ask you for the answer in torr. But when you actually do the equilibrium calculation, you have to actually convert it to atmospheres, do the equilibrium calculation, and then convert it back to torr. So sometimes people think, well, you know, they gave it to me in torr and they want the answer in torr, I could just kind of leave it. But definitely for equilibrium, it should really be in atmospheres as the unit of pressure. Any questions on that? All right, let's do a little bit of calculation. Why not? Equilibrium concentrations of everybody here is something 0.012 molar, 0.054, and 0.14. We're looking for both of them there, the Kc and the Kp. So take a few moments, calculate them both, see what you come. Okay, let's take a look. So in this case, I want to calculate both the Kc and the Kp value. It would make the most sense to calculate which one first. Yeah, because we're given concentration. So with that, we could just go into the equilibrium expression, right? By the way, also, I'm pretty sure it's self-explanatory there, but if you are calculating the equilibrium constant from the equilibrium expression, the concentrations you put in there do need to be equilibrium concentrations. Yeah, so you got to make sure they are equilibrium concentrations. So in this case, we will write our expression, which would be our products divided by our reactants, and in this case, everybody is going to go in. That would get us here 0.14 divided by 0.012 and our 0.054 in this case. And that's going to get us a number with some other numbers. That's like a 216, or if you're a significant figure wise, 220, whichever way you want to go with that, I suppose. That's looks like we've got two everywhere in this case. Any questions on that there? This is a small or large value. Okay. So we should mainly expect reactants or products. Products, right? So now that we do have our Kc value, we use that other equation, which I'm trying to remember right now, that will allow us to go between the two. But I think it is something like this, I hope. Mega memory course is paying off, I hope. All right, so we're looking for Kp. We obviously have our Kc. Remember once again that this R is the one that we do use for in the ideal gas law. And again, not the energy version of it. We also need our temperature to be in Kelvin. So that's a good way to remember. It's like kind of like the ideal gas law, right? A gas law needs to be in sort of Kelvin. So we're going to do a 74 plus a 273 in this case. And that's going to get us here like a 347 Kelvin. We also want to find our delta N, which is our number of moles. And once again, we want to make sure that we do the moles of our products minus the moles of our reactants. So just simply count the coefficient there for anything with a G. That's going to be 1 on that side minus 1 and 1 make 2. Gives us a -1 in this case. And again, that negative is important in terms of the math part of it. I think, if I'm not mistaken, we got everything we need. So we're going to go our Kp in this case, going to be, again, depending on which number you use, I'll use a 220. Why not? 0.08206. We'll do a 347, and it's going to be a -1. So cleaning all that up there, we're going to go 347 times 0.08206 and to the -1, which is basically 1 over it, times a 220. That's 7.7 on the Kp. I think you get like a 7.6 on the Kp if you use 216. So pretty close. Small or large value for Kp? It is still considered a large value. Again, anything over 1 is considered large. So this is sort of what I was mentioning earlier. The numerical values are in most cases not going to be the same, but again, they could be, just so you know. But in a lot of cases, they won't be. But they will tell you, again, the same thing, that in both cases, we have a considered sort of large value of K, which means we should expect mainly products at equilibrium. Yeah. Okay. I would say probably, yeah. So there are a couple of things as we go through this chapter and other chapters, but the K will not have units, but you will be asked as we do equilibrium problems to solve for things like equilibrium concentrations or equilibrium pressures, which when you do solve for those values, you need to kind of put the units back in to what they are. But definitely if you're solving for just K or something like that, or given a K, typically will not have units. So the other question was about the moles. Yeah. Yeah, so really we're just looking, this is really the number of moles of gas molecules, and it's really the difference between the moles of our product side minus the moles of our reactant side. And really, when we go to each of those sides, we want to look for anything with a G and basically just the coefficient. So the coefficient here is 1, so that's where the 1 comes from. On the reactant side, that's a G, and that's a 1, and that's a G, and that's a 1, and that's where the 2 comes from. Yeah. Other questions? Now you could have maybe a mixture where they're not all gases, so make sure you only count the gases, obviously, when you're doing that part. Yeah. Other questions? Yeah. Yeah, so I would say in a lot of cases it's not going to be the same, but it definitely can be. Like I came across a problem a couple of semesters ago where actually I actually made up numbers in a problem once, and I ended up getting actually the same values of KP and KC. So it is possible it does, but in most cases, they typically will be different numbers, but again, they still tell you the same thing. I just threw it out there for significant figure wise since they were all twos. And since we're dividing and multiplying, I know it's like a chemistry class. Every so often I pull out the sig figs, I suppose, yes.
Not sure we're getting, but out of curiosity, so if the temperature wasn't 74 for all, or, what would be like the standard? Like, would you have to calculate on each individually?
Well, to answer your question is, if it wasn't 74 degrees and it was some other temperature, probably your concentrations that you would have at equilibrium would be some different numbers. And that would give you a different value for KC. And then obviously with the temperature changes, if you go to the KP part of it, along with those different concentration values will give you some different values. Yeah. Let's say the first part again, they give you what? Right. But do they give you like the K value or? I argue. I would have to look at, I'm gonna look at it a little bit later, just I'm not familiar exactly with that question or what it's like. Other questions? All right, so let's try another one here and see. And I'm just gonna go with we'll go with this one as NO2. I don't know if it's changed on your paper or not. So in this case, okay, let's take a look since we're getting to the end here. So clearly we're given the KP here. So we'll start with our KP expression. It's going to be the partial pressure of NO. We do need to square it because of the coefficient. We're going to times it by the partial pressure of O2. We're going to divide it by the partial pressure of NO2 and square it. And that's going to equal 158. In this case, we have the partial pressures of NO2 and NO given to us, which means we can put those in the hopefully right spots, 2.27 squared. Partial pressure of O2 divided by 0.4, which we also need to square, and that's going to equal 158. We're going to multiply that to the other side, right? And then come back and divide by the guy on the top, right? So I'm just going to do that all in a single move, perhaps. We're going to take 158 times 0.4 squared. And maybe I'll break it up here so you can see it. 0.270 squared partial pressure of O2 will equal 2528. We're then going to divide this to both sides here. That's going to cancel. So it's going to be divided by 0.27 squared. And that's going to be me a partial pressure here of about 347 atmospheres. This particular case. Now, to sort of answer a question I was asked a second ago, we clearly do need units on this, right? Because we are solving for a pressure, and it would be the same units as obviously the other pressures that were there. As you can see, it's also atmospheres that we see in our expression here. Question on that there. K value in this case is large or small? Pretty large, and that means we should mainly have, and that means probably a majority of the pressure should be on the product side, which I would say at 347 is definitely probably on the product side there with our oxygen. So again, those things, should sort of correlate to each other. Question on KP, KC, how to convert between them. All right, so